All right, recorded is rolling. It is Tuesday, September 13th, and we're going to start on the next section, which is going to involve forces and Newton's laws of motion. So, do you guys have to, gotta zoom out here a little bit. Right, do you guys have the projectile quiz turned in? So some of you guys turned that in yesterday. Going to turn in today. Turn today. So it's due today. Right, and then the main thing we're going to do today is going to be a spring scales lab. Now, before I go over that, I do need to also get you guys a packet of 60 questions on Newton's laws of motion. This is going to be due Friday, September 30th. All right, so while you guys are back there doing the lab, I'm going to staple these together. It's like a mini packet going on. Okay, there's 20 questions on each of Newton's laws of motion, right, first, second, and third. All right, and then on the back page, there's going to be what those laws of motion are spelled out. So there you go. Okay. So again, while you guys are doing the lab today, I'm going to staple these together and put these on your desk, and then you'll have these. And then I'll just pick this up. Well, we're going to go over the answers over the course of the next few weeks, and then I'll pick these up for you guys on Friday, September 30th. Just make sure you're following along, and then as long as you were, turn that in, get those points. There you go. All right. So on your desk should be a page that looks like this. This is a lab page. It's really 10 mini labs. And I want you guys to work with the spring scales and get an idea, maybe look at your hands on these to get an idea of how forces work. Now, a force, here, give you guys a few notes here, just a few short notes here. Okay. Of all of forces, it's just a push or a pull. Okay. Now, so far in this class, the only variables we've worked with are displacement, velocity, time, and acceleration, right? Mass maybe popped up here and there, but now mass is about to be a lot more important. Okay? And masses and forces. So, do you guys know what the unit is to measure force in the metric system?
F.
Okay, so the variable is F. Right? And if you look on the spring scale, well, when you guys get back to the lab area, there's a capital N. What do you guys think capital N stands for? Newton. Yeah. So I'll say measured in newtons, capital N. Okay. And what is 1 Newton? And so 1 Newton is a composite unit. It's the same thing as 1 kilogram meter per second squared. Okay. Now that might look a little convoluted, like what? Why is that? Why is it that when you push or pull on something, you could quantify it in a unit that breaks down into this? Okay. But I think it'll make more sense if I list out Newton's second law of motion, which again, I'm about to get to you guys. What does Newton's second law of motion say? It says this, or oftentimes you could rearrange it, looks like this, where net force, say net force, is equal to mass times acceleration. Okay. Or you could rearrange this and say acceleration is a net force acting on some mass. That's if you do a little algebra switcheroo. You guys see these two lines are the same thing, right? Okay. Okay. But this line matches up really well with these units. Okay. And what this says is if you push on a mass with some force, right? Say I have pick on my lab weights off right here, got this, boom, mass. Okay. I push on it with the force, that's going to cause it to accelerate. Okay. Okay. So if you push on a mass, cause it to accelerate. Okay. Or in this fraction version, if you apply a net force to some mass, it accelerates by some quantifiable amount. You guys see how the units match up with the variables? So force is measured in newtons, mass is measured in kilograms, and acceleration is meters per second squared, which we've been working with for the last few weeks. Okay, you guys see that? Okay. All right. So how about these spring scales? Because I want you guys, when you get your hands on these spring scales, to know how they operate. Okay. Now there are different colored spring scales back there, and each color corresponds to a certain spring stiffness. The brown ones are kind of the best. They're the most versatile. They're kind of in the middle. Have a middle medium stiffness. Now all the brown ones are being borrowed except for this one. So yeah, we've got the ones we have, but the closest ones you guys will have today are the red ones. The red ones are kind of similar to brown, right? But let me go over what's going on here. So the brown ones go up to 10 newtons, right? So if I apply a force, oh look, it'll stretch, right? Hey, do you think if I apply here, let's say I apply some force, it pulls out to 2 newtons. Okay, so 2 newtons, right? What if I apply triple the force? Do you think it'll go to triple the stretch amount to 6 newtons? you guys see how the number of newtons, it's kind of hard to tell, but when you guys get back there, the number of newtons are scaled linearly. So it goes 0, 2, 4, 6, 8, 10, right? And it's scaled linearly like that, right? Yeah, so if you apply triple the force, you'll get triple the stretch, okay? Now, what I'm trying to get at here is one of the things that we're going to be talking about over the next few weeks called Hooke's Law. Hooke's Law, right? And Hooke's Law involves ideal springs. And Hooke's Law says this. If you apply a force to a spring, it's going to stretch by some amount. But here it is in formula form, right? F equals kx. I'll go over it a little bit so you see what's what, right? Let's say there's like a spring, right? It's like this long, and this is like unstretched. And it's unstretched form, it's just hanging around, looks like that. There are no forces on it. But hey, what if I do stretch it? What if I apply a force, right? I start to stretch this thing, right? And then, so in the stretch form, maybe it looks like this, right? Okay, because I applied a force here and an equal and opposite force here. And those two forces have to be equal and opposite. I drew a little force vectors there, okay? Because of Newton's third law, right? Newton's third law, right? I mean, as long as this is in equilibrium, right? But do you guys see how much this has been stretched? Here, like here was the original length of the thing. Here's how much it's been stretched to. So this amount right here, I can call this x, or some textbooks say delta x, like a change in x, right? Right, that's what that x is, right? And this force is what this force is. Okay, so if you apply a force, it's going to stretch some amount. But when you guys get your hands on these spring scales, what you'll notice is that they stretch different amounts for the same force. Like here's how much the brown one stretches if I put some force on it. Okay. The blue one's wacky because watch the little tiny force. Hardly anything at all, hardly any resistance. It's that, okay, this one only goes up to 2.5 newtons. So 2.5 newtons, it maxes out, right? Versus the brown ones go up to 10, so that's like 4 times as stiff. Get that? Okay. And then the stiffest ones you guys have today are these white ones. They go up to 30 newtons. So, right, little bit of force, or sorry, a lot of force, I should say. It doesn't stretch very much. Okay, really stiff. Okay. Now take a look at this equation here, right? Hooke's law, right? Which relates to these spring scales. That's why I'm introducing it to you guys today, right? So you guys know what formulas match up with the tools that you're using today. Okay, so see, I applied forces, and then they stretch different amounts. What do you think that K probably refers to? You guys have any guesses? How about some property of those springs, like maybe how stiff the spring is, right? So here's the applied force, say force, match up with the diagram here. One of these forces, okay. Here's how much it's stretched. I should really say or compressed, although you guys aren't going to be compressing any spring scales today, but in general, okay. And what this K represents is called the spring constant, which is like the stiffness. Like how stiff is that spring? Because you guys got different colored spring scales, they have different stiffness springs. Okay, you guys can get that? Okay. All right, so let's take a look at these 10 mini labs. Now, you guys can put multiple names on a paper. You guys can work in teams on this. Tell you what, if you want extra paper or want to work by yourself, that's okay too. Let me know. I can get you guys extra paper. Okay. But I want you guys to try out these 10 different scenarios and see what actually happens when you apply forces in different directions. Make this chain gang here. Okay. So got front and back side. Right. Let me give you guys a couple of hints, or just to answer some questions that I always get. Right. So number one, see where there's the mass hanging from a spring scale? This one's like the most straightforward. All you do is just hang a mass from a spring scale, right? Treat mass as independent variable for this one. So mass equals independent variable on number one. And you guys know what that means. That just means that you're using different masses. Right, so use different masses. You guys see 4 different masses, and then you can make a graph. If you use 4 different masses, you get 4 different forces. I wonder what that graph looks like. You guys might probably be able to make a pretty solid hypothesis even before you do this one, what that graph is going to look like. Okay. Versus number 2, in contrast to number 1, use the same mass over and over. So number 2, that mass right there, use the same mass over and over. Okay, when having you guys do with number 2, see how there's like one mass hanging from 2 different spring scales? Okay. You guys know if you balance on your 2 legs, you can be evenly distribute your weight, or you can shift all your weight onto your right leg or your left leg, you can shift your weight around. Okay. This is like that, but a tension version instead of compression. Tension and compression are just 2 different variations on forces, right? So these spring scales can be in tension. Do you think you could hold these spring scales? Say they both hook onto a lab weight down here. A lab weight up here. Right here. How about this? Here's my lab weight. Boom. Okay. Think you could shift these around so that maybe the force distributes a little bit more or a little bit less on either spring scale. Right. So then record those numbers and add them up and see what happens. And then I wonder what that graph is going to look like. Right. Then you go through piece by piece and part by part. Remember, there's 10 parts here. So I will walk around, help you guys out with any questions you guys have about this lab. But this is going to be our project today. All right, who's got any questions right now? All right, so I will close out this recording, get you guys going on that. Remember to turn in your projectile quiz if you haven't yet.